I welcome you all in this lecture on system model of robots, which is a part of modeling and simulation of dynamic system course. Here in this lecture next 30 minutes we will be looking at how can we model a robot. As all of you know that a robot is an example of a mechatronic system. Okay. Here you will find the arms of the robot, they have got their own dynamics, okay, and you can say that these are there in the part of the mechanical system. Now, there are actuators which actuate these joints, and this actuation is usually the motors, okay, which we consider to be in the electrical domain. Apart from that, there are going to be say sensors, encoders, potentiometers, vision sensor, there can be many more peripheral things are going to be there. So, it is a true example of the mechatronic system. Now, in this lecture on robots, essentially I would like to take you up to the development of the dynamic equation of the manipulator. But before that I need to give you a little background of the robots and its kinematics, and then we will move on to the dynamics, because without kinematics we cannot go into the dynamics of the manipulator. So, remember our aim here is to develop the dynamic equation for the manipulator. So, the word robot has root in Czechoslovakian language, okay, where the robot which is a Czech word which means work, and robota which is a slave word, it means that menial or slave labor. It got publicity from the play Rossum's Universal Robots in 1921 by Karel Čapek, and first commercial robot came into 1962, and that was by the animation founded by Joseph F. Engelberger, who is called the father of robotics, in 1950, okay, and it was installed in the General Motor plant. There are many definitions for the robot, but I would like to just go through the International Standard Organization ISO definition, which defines robot as automatically controlled, reprogrammable, multi-purpose manipulative machine with or without locomotion for use in industrial automation application. Now, here the word reprogrammable is basically the word which distinguishes the robots from the fixed automation. Okay. Here this device is reprogrammable, whereas in fixed automation the programming is difficult. So, as I was telling you, a robot is an integration of mechanical, electrical and software components. Mechanical, as I said, the arms of the manipulator; electrical means the actuators which actuate the joint of the manipulator, and the software which are essentially the different codes intended for the control of the manipulator, okay, that can be programmed to perform a variety of tasks both with and without human intervention. And robotics is basically the study of this robot design, programming and control. So, before, as I said, moving on to the dynamics, I would like to give you a little background. So, first let us see the mechanics and control of mechanical manipulator. So, here as you can see that a manipulator has been shown, and there are certain objects which are kept in the environment of the manipulator. Now, in robotics we are mostly concerned with the location of the object in the 3-dimensional space, because robot needs to manipulate that object. Okay. Now, this object which is there in 3-dimensional space, that can be described by 2 attributes, and these attributes are the position and the orientation. So, the position of the object, the 3 x, y, z coordinates of the object, and 3 orientations of the object. Okay. Now, in order to describe the position and orientation of a body in space, we always attach a coordinate system to the body, okay, or to that particular object, and then we describe that coordinate system. Okay. And in this process, any frame can serve as a reference system with respect to which the expression for the position and orientation of a body can be described. So, here you can see that we are fixing a frame at the base of the robot, we are fixing a frame at the end effector of the robot, and we are fixing different frames to the objects which are there in the surrounding of the robot. Next important thing is kinematics of manipulator. Now, as all of you know that kinematic is a science of motion that treats motion without regards to the forces which cause it. Okay. So, here within the science of kinematics, one studies position and its derivatives, okay, its higher order derivatives. So, say position, velocity, acceleration, and all other higher order derivative of the position variable, and it could be with respect to time or with respect to any other variable. Hence, as I said, the study of kinematics of manipulator refers to all the geometrical and time based properties of the motion. Now, manipulator which I am going to discuss here, we assume that they are rigid link, because if manipulator links are not rigid, they are flexible, there are different treatment which is to be needs to be given in order to take care of the flexibility of the manipulator. That I am not going to discuss with you today here. Okay. So, here the manipulator consists of nearly rigid links which are connected by joints that allows relative motion of the neighboring links. So, this is what assumptions we are going to make in our this course of study. Now, these joints, as I said, are usually instrumented with position sensors which allows the relative position of the neighbor link to be measured. Now, these sensors could be, as I said, it could be encoder, it could be potentiometer. Okay. Now, in case of rotary or revolute joint, these displacement what we call it as the joint angle, and in case of manipulator, if it contains some sliding joint which we also called as the prismatic joint, the relative displacement between links is a translation, and that we call it as the joint offset. So, first of all, let us see what do you mean by the forward kinematics of manipulator. Here basically we will be seeing understanding what is the forward kinematics and what do you mean by the inverse kinematics of the manipulator. Now, as you can see in this figure, okay, this is a manipulator and we have a coordinate system fixed at the base and one coordinate system fixed at the end effector, which we also call it as the tool coordinate system. Now, you can see that these are the 3 revolute joints and these joint rotations are represented by say theta 1, theta 2 and theta 3, fine. So, the forward kinematics basically means that for these given joint angles, what are the Cartesian coordinates of the tool, okay, of course with respect to a reference coordinate system. So, here the forward kinematics problem is to compute the position and orientation of the tool frame relative to the base frame, okay. This is what we mean, the position and orientation computation of the tool frame with respect to base frame, okay, for given joint angles. okay, or this is what we also call it as the representation of manipulator position from joint space description to the Cartesian space description, and this is what we mean by the forward kinematics of the manipulator. Now, let us see what do we mean by the inverse kinematics of the manipulator. Now, here as you can see in this figure, again manipulator is there, we have the two frames, that is the base frame and the tool frame. Now, the question is that if we have a tool frame position and orientation, if it is known, then we are interested here in inverse kinematics, finding out the different joint angles which will give us those position and orientation of the tool frame with respect to the base frame. Okay. So, here for given position and orientation of end effector of the manipulator, we find out the all possible set of joint angles which could be used to attain the given position and orientation. So, this is about the forward and inverse kinematics of manipulator. Next is the Jacobian of the manipulator. Okay. Jacobian actually specifies a mapping from velocities in joint space to velocities in Cartesian space, and the relationship is something like this. For this manipulator, you can see that the joint space velocities are theta 1 dot, theta 2 dot and theta 3 dot, and the Cartesian space velocities are say angular velocities are omega and the linear velocities are v. Okay. So, here the mapping between this joint velocity vector theta dot and the Cartesian velocity vector v. Okay. This is where the Jacobian comes into the picture. Okay. Here 0 basically means that these are specified with respect to the 0th frame, which is nothing but the base frame which I have talked to you. Okay. So, here we will also see that for a given desired contact force and moment, what set of joint torques are required. If we are interested in knowing that, then there also this Jacobian comes into the picture. Okay. And that relationship is tau is equal to J transpose into F. Okay. So, this is how this comes into the picture. Yeah. Now comes the actual point, that is the dynamics of the manipulator which we are interested in. Okay. Now, as all of you know that the dynamic involves studying the forces required to cause the motion. Okay. Now, you know, in order to accelerate a manipulator, say from rest, glide at a constant end effector velocity and finally decelerate to a stop, a complex set of torque function must be applied by the joint actuators. Okay. Then only this type of motion of the end effector is possible. Now, the exact form of this required function of actuator torque depends on the spatial and temporal attributes of the part taken by end effector as well as the mass properties of the links and the payloads. Okay. Friction in the joints and so on. So, so many things affect the dynamics of the manipulator or the exact torque requirement of the manipulator. Now, these manipulators, as I said, needs to be controlled. Okay. Because we want to apply an appropriate torque here, okay, for a given trajectory to be followed by the manipulator. Now, one method of controlling a manipulator to follow a desired path involves calculating these actuator torque functions by using the dynamic equation of the manipulator itself. Okay. So, if we do that, we can control the manipulator appropriately. Okay. Now, these dynamic equations of the motion of the manipulator can be used for two purposes. Okay. The first purpose, what I just talked to you, that we calculate the torque required for the desired motion, and this is what we call as the inverse dynamics problem. Okay. And the other purpose is could be the simulation, that is, if you are given the joint torque, okay, we can find out what are the acceleration, velocity and the displacements. So, find acceleration in terms of torque and then calculate displacement, and this type of problem is what is called as the direct problem. Now, to deal with the dynamics of the robot, there are three ways by which it can be done. Okay. The first way is the Newtonian method. Okay. Now, this method is essentially based on the concept of force and moment balance. Okay. So, we have the force balance, calculate velocity and acceleration and use to get the forces. Okay. And another method is the Lagrangian method. This method is the energy based method and it calculates potential and kinetic energy of the robot. Okay. And these kinetic and potential energy terms can be used to calculate the Lagrangian, which is nothing but kinetic energy minus potential energy, and when this Lagrangian is substituted in the Lagrange equation, you get the joint torque or the joint forces. Okay. And from here we can determine these torques and forces directly. Okay. The another method is the bond graph method. We have already seen how to derive the system equations using bond graph. So, the bond graph method can be used to first draw the bond graph model of the robot and then we can derive the system equations of the robot algorithmically. Okay, using the algorithm that is what the elements gives to the system and what does the system gives to the integrally causal storage elements. If we apply that algorithm, then we can get the system equation automatically from the bond graph. Now, before we proceed, a small discussion about inertia, because we are talking about dynamics and without inertia dynamics is meaningless. Okay. So, a little discussion on the inertia. Inertia is a tendency of a body to remain in a state of rest or uniform motion. Okay. A force is required to change this state. Now, the motion could be linear or rotational. Linear inertia is known as mass and the frame in which the inertia is measured is known as the inertial reference frame. Center of mass, the point in a body that moves in the same way that a single particle subjected to same forces would move. Okay. And this way we can evaluate the center of mass. Moment of inertia and mass. If a object has a mass m, the mass is distributed throughout the body, and for a single degree of freedom I did not talk to you, but degree of freedom, as all of you must be knowing, is the number of independent variable required to specify any object. Okay. So, for a single degree of freedom we can speak of just a mass for linear motion. For rotation, the equivalent term known as mass moment of inertia, and a body has got 3 mass moment of inertia and 3 mass product of inertias. Now, the mass moment and mass product depends on the shape and mass distribution of the body. It is convenient to create a matrix that represents the inertia of a body, and this matrix we call it as the inertia tensor. Okay. So, here you have Ixx, Iyy, Izz terms and other are the cross terms. Now, when we select a reference frame such that the product of inertia, these product of inertias are 0. In such case, the moment of inertia are known as the principal moment and the axis as the principal axis. Now, we can transfer or you can find out moment of inertia about any other axis using the parallel axis theorem. Okay. So, these are the basic concepts of the mechanics, which I hope all of you must be knowing. Okay. Now, let us look at the ways of finding out of the dynamics equation of the manipulator. First, as I said, Newtonian method. So, here first iterate out the serial change of the robot starting at link 1 and continue to link I minus 1. Here what we do is that calculate the linear and angular position, velocity and acceleration of the center of mass of each link, and then once these are there, the acceleration and velocities of the center of mass are calculated, we can use the Newton-Euler equation to calculate the force of the forces on the center of mass of each link. So, this is for the linear motion and this expression is for the angular motion. Okay. Now, once we have the forces, we can work back from the last link to calculate the joint forces and the torque. Okay. We can include gravity load by giving frame 0 an acceleration of say g. Now, this fictitious acceleration causes the same reaction force and torques at the joint as gravity without additional computational requirement. The expressions are usually written in the form of state space, and this describe basically the instantaneous position, velocity and acceleration, and can be for each joint, can be for Cartesian coordinates, and of course, this is important for the advanced control analysis. Next method which I would like to describe is the Lagrangian way of finding out the dynamic equation of the manipulator. Okay. So, in Lagrangian method we know that first we evaluate the kinetic energy. So, work required to bring a body to rest, which we call it as kinetic energy. So, for linear motion this is half mv square, and for angular rotary motion this is half I omega square, and the potential energy is the energy due to the removal of an object from the origin of its reference frame, say gravitational or spring. So, for gravitational this potential energy is mgh. Now, this Lagrangian is defined by k minus u. So, L is k minus u, okay, and we can get the torque of force of joint N from this equation. Okay. So, this is d by dt of del L by del q n dot minus del L dl by dq n is equal to f n, okay, where basically this q n is the generalized coordinate. So, we can find out basically if we talk about the manipulator, we can find out the kinetic energy of the link. So, this is translational kinetic energy and this is rotational kinetic energy for say ith link, and then we can add up all the for kinetic energy for all the link and we can get an expression for the total kinetic energy. Likewise, I can find out the potential energy for the ith link here, and then the manipulator potential energy can be found out by summing the potential energy of all the links, and then we can get the torque expression for the manipulator this way. Here I am just substituting for L. Okay. So, the manipulator expression finally it comes out in this form. Manipulator dynamics equation in the joint space comes out in this form, okay, where M is the mass matrix, V has got two elements, the Coriolis which is a function of two different velocities, and the centrifugal which is a function of velocity square. We have the g theta, that is which contains the gravity terms also. Okay. Here we can add up even the friction term, okay, that also can be added up. Similarly, we can write the expression in Cartesian space this way, okay, and we can convert back to the joint space using this equation which I discussed you some time back, that is torque is equal to Jacobian transpose F. So, if we compare these two methods, the Newton-Euler is computationally better, okay, but Lagrangian equation gives more information. Let us take an example. Okay. So, suppose I have got say pendulum here, basically a mass m at the end of a say link of length L, and here to actuate this joint I have got a torsional spring. Okay. So, this torsional spring actuates this joint. We can always replace this torsional spring with the help of a motor. Okay. So, there, but here my aim is to explain you how we model it. Okay. So, I am just considering actuation of this joint with the help of a torsional spring. So, let us use the Euler-Lagrange formulation to find out the dynamic equation for this one. Okay. So, you can see the kinetic energy for this case is half ml squared theta dot square, basically this is half I omega square. So, for I for this case is ml square. So, we have the half I omega square term. Assuming y is equal to 0 as the datum, the potential energy can be given by half kT theta square, that is the energy is stored in the spring, and minus mgl theta, because this length is going to be L sin theta. So, minus mg into L sin theta. Now, I can we have this as the Lagrange equation. Okay. So, in order to get here, I find out the L, which is t minus u, and I substitute this t minus u here in this equation. I get Lagrange equation in terms of t and u, that is kinetic and potential energy. Now, here the generalized coordinate in our case is theta. So, this is going to be the Lagrange equation here. Now, if we know that our t has been half ml square theta dot square. So, I can find out del t by del theta dot this one, then I can find out d by dt of this one, which is ml square theta double dot, then I evaluate this term which is 0 here, then we know the potential energy here. So, I can evaluate del u by del theta here, this one, and when I substitute all these terms in this equation, this is what we get, ml square theta double dot plus kt theta minus mgl cos theta is equal to 0. So, this way we derive the system equation for this robot. Okay. So, that was using the Lagrangian method, where we found out the kinetic energy, we found out the potential energy, we found out the Lagrange, and then we substituted it in the Lagrangian equation, and we got the system equation for the robot. Now, if I do it using the Newton's method, then here we can see that the restoring torque, this weight is mg, force is mg. So, this is mg, this force is going to be your mg, this is mg sin 90 minus theta, which is basically the this one, this term, and the torque term because of the spring. So, minus kt into theta, and this unbalanced torque is responsible for the acceleration of this point mass here. So, that we equate it to I alpha. Okay. So, ml square theta double dot is equal to this, and this way we get the same equation. Okay. So, here basically what we have done, we have found out the unbalanced torque, and that torque is going to be responsible for the acceleration of that joint, and we have equated with the inertial torque. Okay. So, this is what is done in the Newton's method. We can also use the bond graph model. Okay, we can draw the bond graph model for this robot. So, for that we need to just find out the position velocity of the tip in x and y direction, and then we can draw this bond graph model. I am not explaining you, and I am leaving it as an exercise to you, but this is the bond graph model which you are going to get for this case. Next, next two example I will just explain to you how we can do that. Next, let us consider this problem. This is a 2 degree of freedom. First degree of freedom is rotation, and second degree of freedom is here through the prismatic joint. Okay. So, for this we have the inertial properties given, say I1 is given about the center of mass of the link 1, and I2 about the center of mass of the link 2, this is given, and if we use the same Lagrange dynamic equation, find out the kinetic energy, find out the potential energy, okay, find out the Lagrange, and then write the Lagrange equation for the in terms of the generalized coordinate. Here we are going to have the two generalized coordinate, one is this joint rotation and another is this joint linear motion. Okay. So, if you do that, this is the result which you are going to get. Okay. So, I am not explaining you because of lack of time here, but this dynamic equation or system equations which you are going to get. I have already talked about Newton-Euler formulation, okay, and I have told you that the algorithm is composed of two parts. First we calculate the angular velocity and acceleration of each link, then we calculate the linear velocity and acceleration of the center of mass of each link, and once the acceleration and velocities of the center of mass are calculated, we use the Newton-Euler equation to calculate the forces on the center of mass of each link. And once we have these forces, we can work backward from last link to first link to calculate the joint forces and torque. This I have already explained how we can take case of the G of the manipulator. Now, for the case of 6 link manipulator with all rotational joints, the equation can be summarized as follows. So, these are going to be the set of equation which we call it as the outward iteration for I is equal to 0 to 5. Basically, here we find out the angular velocity, you can see for the ith link, I plus 1th link expressed in terms of I plus 1th frame. Then we are finding out the angular acceleration. Here we are finding out the linear acceleration of the origin of frame of I plus 1 with respect to I plus 1. Then here we are finding out the acceleration of the center of mass. Then here we are calculating the inertial forces and we are calculating the inertial torque. Okay. So, this is what is done in the outward iteration, and here then we go for the inward iteration, that is I is equal to 6 to 1, and here we calculate the forces in the links and the torques in the links and moments in the links, and then we find out the jet component of that, which gives us essentially the joint torques. And this is the last example which I will just explain to you. Again, I am not doing this problem, you can use the same algorithm which I have just explained to you using that is the Newton-Euler equation. So, this is a 2 link manipulator. The modeling can be simplified by assuming the point masses here, the M1 and M2, the link lengths are L1, L2, say these joints are theta 1 and theta 2. Okay. Then the problem is to find out the joint torques tau 1 and tau 2. So, if we apply the same algorithm, these are the values which we are going to get for the first joint torque and the second joint torque. Okay. So, That is all, and you can refer our book for further study, and there is another very popular book by Professor J. Craig and which is published by the Pearson, that also you can refer, and that will help you in understanding the modeling of the robots. Thank you.